Dear BSc second year, semester third students, myself Satish Kumar Kamble, an assistant professor, Department of Physics, Avasar Marathi, Arts and Newcomers Science College, Rajapur. In the last video lectures, we have studied uh, the unit third of paper third, applied physics, that is the properties of material. In that unit, in this unit, we have studied the chapter first, electrical properties. Then we have started the optical properties. Now today we are going to deal with the optical properties of the material. Okay. So in the last lectures we have studied, we have introduced the optical materials. Again, we have studied all these things here. That is the interaction of photons, that is electromagnetic radiation, with the solid, that is the atoms, ions, or the electrons of the solid. That is the interaction of photons with atoms, ions, or electrons of the solid causes the process of absorption or reflection or the transmission. Again, in the last video lecture, we have studied refraction process, okay, in which we have studied the theme of refractive index and the Snell's law. Now, today we are going to study the process of reflection. So, uh, So reflection is caused due to the interaction of the electromagnetic radiation or the photon with the valence electrons of the solid. Now, when a beam of protons, strikes the material, then there is an interaction of the photons with the valence electrons. Again, photons give up their energy to the electrons. So, in metals, the radiation of the almost any wavelength excites the electrons into higher energy levels. If no light is reflected, that is, photons are totally absorbed, then the metals would appear black. In aluminum or silver, however, photons of almost same wavelength are immediately emitted as the excited electrons return to their lower energy levels. That means reflection occurs. Okay, this is observed for entire visible electromagnetic spectrum. Therefore, these metals appear to be white or silver in color. Now, the term reflectivity, that is capital R, is nothing but the fraction of incident light that is reflected. So, reflectivity is related to the reflectivity is related to the refractive index by the relation capital R equal to n minus 1 divided by n plus 1 whole square. This is the relation of the reflectivity and the refractive index if the material is in the vacuum or in air. Okay, and the relation between the reflectivity and the refractive index when the material is in some other medium with refractive index Ni, then this relation is there. R equal to n minus Ni divided by n plus Ni whole square. It is for when the material is in the some other medium with the refractive index Ni. Okay, these equations are valid for a reflection from single surface and for perpendicular incidence of radiation. The value of reflectivity capital R changes with the angle of incidence. Again, materials having higher index of refraction, that is, materials of highest refractive index may have higher reflectivity than the materials with the low reflective index. Okay, so reflectivity also changes with the wavelength of the incident radiation. Again, the reflectivity of the, for example, typical glass is about 0.05, while for metals it is typically of the order of 0.9 to 0.95. So, due to high reflectivity of the metals, they are opaque to radiation. Okay. Here we can see here the reflectivity of the typical glass is of about 0.05, whereas the same reflectivity for the metals is of the order of 0.9 to 0.95. Okay, so reflectivity of the metal is much higher than the reflectivity of the glass material. So due to this high reflectivity of the metals are opaque to radiation. Okay. The applications where high reflectivity materials are required include, for example, certain type of coating on the glasses and mirrors. Many such coatings have been developed for glasses. There are also applications where reflectivity of the material must be extremely limited. Again, such coatings are known as they are known as anti-reflective coatings. Okay, anti-reflective coatings. Glasses with such coatings are used uh, in automobile rear view mirrors. On again, they are used on windows and photo frames. Now let us talk about the absorption. Here the interaction is nothing but the photon, that is the electromagnetic radiation, with the structure of the material. Now uh, when the radiation is incidenting on the surface of the material, the portion of the beam, the portion of the beam of electromagnetic radiation which is not reflected is either absorbed or transmitted to the material. The fraction of the absorbed beam is related to the thickness of the material and the manner in which photons get absorbed sorry, and the manner in which photons interact with the structure of the material. The intensity after passing through the matter is given by I equal to I naught exponential of exponential I equal to I naught e raised to minus alpha x. Okay. Where here is the intensity after passing through the matter. It is given by this equation I equal to I naught e raised to minus alpha x. Here x is nothing but the path through which photons move, which is usually the thickness of the material. Here alpha is the linear absorption coefficient of the material, and it is the intensity of the beam after uh, reflection at the front surface, and I naught is the intensity of the beam when it reaches the back surface. Okay. Again, absorption in materials occurs by several mechanisms. For example, first is by Rayleigh scattering, or in other words, we can say by elastic scattering. Here, in this case, the photons interact with the electrons which are orbiting in an atom and are deflected without any change in photon energy. Rayleigh scattering is more significant for higher photon energies and is responsible for the color of the sky. Okay. Relay scattering or the elastic scattering also depends on the particle size and is most efficient for the particles that are much smaller than the wavelength of the light. Now the second case, uh, Compton scattering. Here also the photons interact with the electrons orbiting in an atom some but loses some of its energy to the electrons. The wavelength of the light increases. This is the example of inelastic scattering. Okay. Again, third one is the photoelectric effect. The third mechanism is nothing but the photoelectric effect. This effect occurs when energy of the photon is fully absorbed and results in the ejection of the electron from an atom. The atoms therefore gets ionized. No electrons are ejected when incoming photons have energies less than the electron binding energy, regardless of the intensity of the light. So the coefficient of linear absorption depends on wavelength of incident radiation and normally increases beyond absorption age. So this was all about the absorption and reflection. Now, after this absorption and reflection, we will discuss about the transmission. Okay. So transmission, the fraction of the incident beam. Here you can see the figure here. The fraction of the incident beam that is not reflected or absorbed is transmitted through the material. Okay, here the transmitted beam is shown here. Here the upper surface of the material, here is the lower surface of the material, and the incidenting radiation of intensity I naught is falling on this upper surface of the material. So here the medium is changed, so the direction of the photon beam also changes. Okay, depending upon the value of the refractive index, the bending is there. Okay, again, if there is no partial reflection, or if there is no partial absorption, then this beam will get transmitted here. So the fraction of the incident beam that is not reflected or absorbed is transmitted through the material. Now let I naught be the intensity of the incident radiation. Then loss due to reflection at front face or the upper surface of the material is R into I naught. Okay. Then the fraction of the incident beam that actually enters the material is nothing but I after reflection, it is equal to 1 minus R into I naught. Okay. Again, the part of the beam that enters the material is lost by absorption. If the thickness of the material is X, here you can see here the thickness of the material. If it is X, then intensity after absorption will be equal to 1 minus R into I naught into e raised to minus alpha x. Okay. Again, actually, before the partially absorbed beam exits the material, actually before the partially absorbed beam exit the material, reflection occurs. Okay, reflection occurs which is at the second the lower surface, which is at the lower surface. Okay, so actually before the partially absorbed beam exits the material, then the reflection occurs at the back surface. This fraction of the beam that reaches the back surface and is reflected is nothing but I reflected at back surface is equal to R into 1 minus R I naught e raised to minus alpha x. Okay. Further, the fraction of the beam that is completely transmitted through the material will be then given by the equation I transmitted, which is equal to I after reflection minus I reflected at back. Okay,